let's look at solving some trig equations that involve nonlinear expressions of our trig function. So for example, we might have like a cosine squared, or we might have a product of trig functions like tangent times sine. Okay, and so usually this is going to involve some algebraic techniques. Primarily, we're probably going to do some factoring. So let's try a few examples here. Our first one is we have 2 cosine squared of x is equal to cosine x. Okay, so just to kind of step aside and just on the side here, I want to work through a similar example and show what we don't want to do. So let's get rid of ignore the cosine for the moment and just think like if we have 2x squared is equal to x. Okay, so if we had 2x squared is equal to x, it might be really tempting to divide both sides by x, and that leaves me with 2x is equal to 1, which means x is equal to a half. And that is one of our solutions, but we're missing a solution. Okay, so what if we did that same equation, 2x squared is equal to x, but instead of dividing, we factor. So if I have 2x squared is equal to x, if I then subtract the x to the other side, so we have 2x squared minus x is equal to 0, and then I factor out an x, that leaves me with x times the quantity 2x minus 1 is equal to 0. And those two factors, the first factor x, I know that means x has to be 0. And the second factor, 2x minus 1, is also going to result in an x is equal to 1/2. So if I divide, I lose out. I eliminate that x equals 0 solution. So we want to be really careful about dividing both sides of an equation by any expression that has a variable in it. Okay, so that means in our equation that we're actually trying to look at here, 2 cosine squared x is equal to x. Again, it might be tempting to just divide both sides by cosine x, which we could do, but you're going to lose a solution if you do that. Okay, so instead, do not divide by cosine of x. We want to move the cosine x to the other side by subtracting it and then factor. Okay, so 2 cosine squared x is equal to cosine x. If we subtract the cosine x to both sides of the equation, we'll be left with 2 cosine squared x minus cosine x is equal to 0. Okay, and so now we can factor out a cosine x, and we're left with cosine x times 2 times the quantity 2 cosine x minus 1 is equal to 0. And then just like I did with the algebraic method here, again, we don't want to divide by that x. We can factor and take each of the two factors and set them equal to 0. So we have cosine x times the quantity 2 cosine x minus 1 is equal to 0, which means I could split that up. So the cosine x has to equal 0, or the 2 cosine x minus 1 has to be 0. Okay, so I've actually taken a quadratic equation and broken it down into 2 linear equations. And we can solve the linear equations like we saw in a previous video. Okay, so the cosine x, let's put a pin in on that one for a moment. And let's go to the 2 cosine x minus 1. To solve this one, just like we did with the sort of algebraic quadratic equation here, we can add a 1 and then divide by 2. And so we're going to get cosine of x is equal to a half. So I have taken the quadratic equation and converted it to 2 linear equations. One equation is cosine x equals 0, and the other equation is cosine x equals a half. So now I need to find the solution for both of those. So cosine of x is equal to 0. When cosine is equal to 0, remember on the unit circle, cosine represents the x-coordinate. So we want the points on the unit circle where the x-coordinate is 0, and that means those points are actually going to be on the y-coordinate, or sorry, on the y-axis. So that means we're going to have x is equal to pi over 2, or 3 pi over 2. And then we can also look at where cosine is a half. Remember, cosine is positive in the first and fourth quadrants. So what angles make cosine a half? Well, in the first quadrant, that's going to be pi over 3. And in the fourth quadrant, that's going to be 5 pi over 3. Okay, so in addition to the pi over 2 and the 3 pi over 2 angles, we are also going to have pi over 3 and 5 pi over 3. So we actually are going to have 4 answers. And again, these 4 answers are only the specific ones on the 0 to 2 pi interval. I also want to be able to express what the infinitely many solutions look like as we rotate forever around the unit circle. They're always going to be coterminal to these, which means they're always a distance of 2 pi away from each other. So I need to take each one of these and add a 2 pi k to it. So x will be pi over 2 plus 2 pi k, 3 pi over 2 plus 2 pi k, pi over 3 plus 2 pi k, or 5 pi over 3 plus 2 pi k. All right, so that would be the solution representing all possible solutions as we rotate around and around forever. Now, it is possible to simplify those a little bit. For example, the pi over 2 and the 3 pi over 2 angles, those are always going to be a half of rotation around the unit circle from each other. So I could actually take those two, the pi over 2 and the 3 pi over 2, and merge them into just one statement, one expression where we say pi over 2 plus pi k. I don't have to do that, but you could potentially see that written elsewhere. So pi over 2 plus pi k, because you only have to travel half the circle to get to the next one. Okay. All right, let's try another one. This time we have tangent of y times the sine of y is also equal to the sine of y. So this will work similar to the last example. Again, when you see this, you might be tempted just to divide both sides by sine of y, but don't, because if you do, just like we saw before, you will lose solutions. So we always want to think about combining or moving terms over, setting it equal to 0, and then factoring. Okay, so let's do that now. So we're going to have tangent of y times the sine of y minus the sine of y, and that's going to be equal to 0. And now if you look at this, we have two terms. We can factor a sine out of both of those. So we'll have the sine of y times the quantity tangent y minus 1, and that's equal to 0. And then we can go ahead and take each of those factors and set them equal to 0. So we'll have the sine of y is equal to 0, or the tangent of y minus 1 is equal to 0. And that equation, we could solve for tangent of y is equal to 1. So again, we've taken a nonlinear equation of trig functions, and we've factored them and rewritten them as two separate linear equations. And so now I can take these linear equations and again apply the unit circle. So where is sine equal to 0? Remember, sine is the y-coordinate on the unit circle, which means we're looking at the points on the x-axis. Okay, and so that's at 0 and at pi. So sine of y equals 0 at y equals 0 and pi. Don't get confused with the y here. I'm using y instead of x as my variable in this equation. That y is not the y on the unit circle. It's actually the angle on the unit circle. But we can use any variables we want, any letters we want in these equations. We don't always have to use x. We could use y. We could use theta. Any letter you want, we could use here. Okay. All right. The second equation, tangent of y is equal to 1. Again, tangent is equal to 1 when the x and the y coordinates on the unit circle are the same. And that happens in the first and the third quadrant at pi over 4 and 5 pi over 4. Okay, so in addition to our 0 and pi solution, we're also going to have solutions at pi over 4 and 5 pi over 4. Okay, so 0, pi, pi over 4, and 5 pi over 4. These are all the solutions on the 0 to 2 pi interval. Now, if we want to, again, list out the specific ones, then we need to add, for any solution that came from the sine, we need to add a 2 pi k. For any solution that came from the tangent, we can just add a pi k. So we get y equals 0 plus 2 pi k, and pi plus 2 pi k, because those come from the sine. And then from the tangent, we only need to use one of them. So we'll take pi over 4 plus pi k. And again, I only have to use the one, the pi over 4, I'll use the smallest one. Now we only have to do that, use that one value, because if you take pi over 4 plus pi, you actually get the 5 pi over 4. So that second value is already included in our expression. Okay, so this would express the infinitely many solutions. And again, you might see this reduced even further. For example, the 0 plus 2 pi k and the pi plus 2 pi k, those are both going to generate all the pi's. So you could actually, you don't have to, but you might see this expressed where we take those two, the 0 plus 2 pi k and the pi plus 2 pi k, and we just merge them together. So again, just to see this on the unit circle, we have 0, and then we're going to go around the unit circle and we're going to land it 2 pi, and then 4 pi, and then 6 pi, and so forth. And then we also have pi, but we're going to go around the unit circle and end up at 3 pi, and 5 pi, and 7 pi, and so forth. So we're always going to be getting values of pi. So just again, that's sort of the visualization. So I could take 0 plus 2 pi k and pi plus 2 pi k and merge those together into a single expression where I'm just adding pi k. And I don't even need to include the 0, so I can just say y is equal to pi k. That includes every odd and even multiple of pi. So that's every time it hits the x-axis. And then I could combine with that the pi over 4 plus pi k. Again, you don't have to do that, but that's another way that you might see the same set of solutions, but expressed with a more simplified expression. All right, let's try one more here. So we have the sine squared of alpha plus 2 sine alpha minus 3 is equal to 0. So this one, again, is a nonlinear equation using our trig functions using sine. It's nonlinear because we have the sine squared. So it might help if we think of solving this first, just as a normal algebraic equation. So replace all the signs with just x. If I had x squared plus 2x minus 3 is equal to 0, how would you solve that? How do you solve quadratic equations? Well, you can try factoring. You can solve it with the quadratic formula. You can use completing the square. So there's a bunch of different ways we can do that. So usually factoring is the easiest. So let's try that here. If factoring doesn't work, you definitely can always resort to completing the square or the quadratic formula. But if we wanted to factor, so x squared plus 2x minus 3 is a quadratic that will factor into 2 parentheses. It's a trinomial, so we'll factor into 2 parentheses. And we have to have it equal to 0. If it's not equal to 0, don't bother factoring yet. So to factor, the first term in each parentheses has to multiply to give you x squared. So that means the first terms has to be an x and an x. And then the second term in each parentheses has to multiply to give you a 3, which means one of the values is a 1 and the other is a 3. It is a negative 3, right? So that means that one of either the 1 or the 3 is positive and then the other is negative. Okay. And then the other piece that we need is when we add, if we were to FOIL this back, so if we've multiplied the outer x times 3 and the inner 1 times x, and then we combine those values together, it has to add to be a positive 2x. So if they're going to add to be a positive 2, we need the bigger number to be positive. So I'm going to make this x plus 3 and then x minus 1. And so then again, we can solve it from there. We'll just get x is equal to 1 or x is equal to a negative 3. We can do the exact same thing with our trig function. So if I have sine squared alpha plus 2 sine alpha minus 3 equals 0, this is a quadratic equation, a trinomial, so we can factor it into 2 parentheses, and it's equal to 0 still, which again, it has to be equal to 0. So the first term in each parentheses has to multiply to give me sine squared alpha. So that means the first term in each parentheses has to be a sine of alpha. And the last number in each parentheses has to multiply to give me a 1, or has to multiply to give me a 3, which means it's a 1 or a 3. And the 1 and the 3 have to add together to be a positive 2, right? So that again means that the 3 has to be positive and the 1 has to be negative. Okay. If we take those factors and set them each individually equal to 0, then we get the sine of a is equal to 1, or the sine of a is equal to a negative 3. Okay, so we've taken this quadratic equation, and just like we've seen in the previous examples, we've reduced it from quadratic to 2 separate linear equations. Okay, and then we can solve each of those separately. So when is sine of alpha equal to 1? Sine is the y-coordinate. Sine is equal to 1 at the coordinate 0, 1, which is on the y-axis, and that happens at a pi over 2 angle. So I know alpha has to be pi over 2. And then the other equation is sine of alpha is equal to a negative 3. Well, I know the range for sine is negative 1 to 1. Okay. It never goes down to a negative 3 or up to a positive 3, right? It's always between negative 1 and 1 because that's the highest and lowest points we ever get on the unit circle. So it turns out that this sine of alpha equals negative 3 has no solution. So all we really have as a solution to this problem is the alpha equals pi over 2. And again, that's the solution on 0 to 2 pi. So how do we express the fact that there are infinitely many solutions as we rotate around and they're all coterminal pi over 2? We're going to say alpha is equal to pi over 2 plus 2 pi k.